Hello class. In this lesson, what we're going to be talking about is optimization problems. So this is when we use calculus to solve problems which involve finding a local maximum or a local minimum. And in this video, I'm also going to be showing you how to use your CAS calculator to do calculus. So with all that being said, let's get straight into our very first question right here, which is asking us the following. A piece of paper measures 20 by 30 centimeters, has squares cut out of the corners, and the sides are folded up to make a box. What size square should we cut out to make the volume of that box as large as possible? So on the face of it, this is quite an intimidating question, but let's just take it slow and first by visualize what we're given. And that's a really good thing to do when we're given optimization problems. You first want to give a sketch of what we're dealing with. So we know that we're dealing with a piece of paper. So that's what I've drawn right here, a piece of paper, and we're told the dimensions of this piece of paper. It's 20 by 30 centimeters. So let's put that information in here. So this right here will be 20 centimeters. And this right here will be 30 centimeters. So let me write 30 here. Now, what else are we told? We are told that squares are cut out of the corners. So let's draw in that piece of information as well. We know that we're going to cut out squares from the corners. Now, what do we know about squares? We know that squares have the same length and width. And you'll probably think to yourself, why are you telling us something so obvious? Well, that's going to come into play later. So just store that away in the back of your mind. So right now we're cutting out squares from the corner. Well, why are we doing this? Oh, that wasn't too good. Let me try that again. Squares from the corners. The reason why we're doing this is because we want to fold up the piece of paper to make a box. Now, this last sentence here is the real important sentence. It's saying, what size square should we cut out to make the volume of that box as large as possible? So in other words, we have to figure out what the size of the squares are going to be. So that means we're going to be changing the size of the squares. It's going to be our variable. So let's assign it a variable. Let's say that the size of the squares, the length of them is x. Now remember, the length and width are the same. So let's just call it x on both sides. So x, 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 x. We're trying to figure out what the size of x will be in order for my volume of the box to be the biggest. So let me say that again. We're trying to figure out what does the size of these x's have to be in order for the volume of the box to be the biggest. So if we're dealing with the volume of the box, what we're going to need are some dimensions for this box. We're going to have to figure out what the height is going to be. What will the height be? We will have to figure out what the width of the box is going to be. And we're going to have to figure out what the length of the box is going to be. And if we multiply all those together, we will end up with the volume of the box. So let's see if we can figure out what these dimensions are going to be. Hopefully you can immediately tell me what the height of the box is going to be. Obviously it's going to be x. And this really just comes to kind of understanding what, if you visualize folding this box up, what's it going to look like? Well, if we fold it up, that means the x value here is going to be the height. What is the width of the box going to be? Well, the width of the box is going to correspond with this region right here, this region right there. So this side length right here will be the width of the box. And we know that the entire width of the piece of paper is 20, but now we're subtracting both of these squares from either side. So it's going to be 20 minus 2x. So I can come over here and I can write 20 minus 2x. So too, we know that the length of this box is going to correspond with this side right here. That is so ugly, but I can't highlight nicely down, which is just not the greatest in the world, but I'm just doing the best I can. There we go. That is as good as it's going to get. These sides are going to correspond with the length of the box. And we know it's going to be 30 because that is 30. The whole thing is 30 minus 2x because of the squares yet again, minus 2x. So now I could come over here and say, well, this is going to be 30 minus 2x. Now that I've done that, what I can now do is write down what the volume of the box is going to be in terms of x. So v of x. I know it's going to be the height, so x, the height of it, times the width times the length. So I'm going to multiply it by 20 minus 2x. And then lastly, I'm going to go 30 minus 2x. All right, fantastic. We are doing such a good job right now. Now, remember, the question is asking us to find when the volume is going to be the largest. So obviously, this is going to be where I get a maximum. And obviously, because we've been talking a lot about calculus, we know a very important property about maximums, and that is that they are a stationary point. They are a stationary point. So in order to find what the stationary point is going to be, we're going to have to differentiate this. That is what we're going to have to do. Now, before we perform our differentiation, let's just expand out our brackets here. So we're going to get v of x is equal to x. Now, I'm just going to leave this x here and just expand out these brackets. 20 times 30 is going to be 600. Then I'm going to get 20 times minus 2 is going to be minus 40x. Then minus 2x times 30 is going to be minus 60x. And then finally, minus 2x minus 2x will be plus 4x squared. Perfect. Let me now just bring my x squared term to the front and do some tidy up. So let me just leave that for the time being. It's going to be 4x squared. Minus 40x minus 60x will be minus 100x. And then finally, I have my plus 600. Then what I'm going to do is distribute out this x in the front. So it's going to be 4x cubed minus 100x squared plus 600x. And then finally, I can now differentiate this. So f dash of x is going to be 12x squared minus 200x plus 600. Perfect. We have now differentiated it. In order to find my stationary points, I know that my stationary points exist when the gradient is 0. So I set my derivative equal to 0 and I solve for x. So 12x squared minus 200x plus 600. Now, we can't do this by hand. We're going to have to use our CAS calculator. And as you remember at the start of this video, I said we're going to be learning how to use our CAS calculator to solve these type of problems. So let's bring up our CAS. And what I want to show you as well is how we could actually start with, oh, let me come over here again. Let me bring this over like this. Perfect technology. Don't you love it? Let's start off with v of x. And let me show you how we could use our CAS to differentiate what we started with. So we wouldn't have to go through this process. We could simply use our CAS to differentiate v of x to get v dash of x. So how could we do that? The first thing that we're going to do is just define v of x, because that would just make our life that little bit easier. So I'm going to start by typing in define. Oh, not over there. Over here. Define. Oh, come on, you can do it. Define. There we go. Sorry about that. Define. And I'm defining v. I just had a terror moment. I'm like, oh no, I'm going to have to start this video again. Is equal to x 20. Oh, I have to go multiply 20 minus 2x 30. Whoop, too many brackets. 30 minus 2x. Hit enter. Now that is defined right there. So now what I do is I'm going to differentiate that. So I'm going to go menu, calculus, derivative. Then I'm differentiating in terms of x, so I put an x there. And now I just have to go v of x. And I can hit enter, and it just differentiated it for us. And as you can see, this right here is what we got here, 12x squared minus 200x plus 600, 12x squared minus 200x plus 600. Remember, we got to this stage right here. We were able to do that. And then we said, well, now we have to solve for it we have to find what my x values are going to be when my derivative is equal to 0. So what we're going to do now is we're going to solve. So I type in solve into my CAS. Then I'm going to open brackets. I'm going to put in this. I'm going to go let the derivative equal 0. I want to know what my x values are going to be. So comma x, close my bracket, hit equals. That is disgusting. I do not want that. I want approximate values. So let's come up here. Let's hit enter again just to bring it down. And then what you do is you go hit control enter. And there we go right there. Okay, so let's now come over here and let's write down what those values are. So we have x is going to be equal to 3.92, and let me round. Let me say this is 24, or x is equal to 12.747 because it's, sorry, 3. I can't count. 3. All right. So we just found the stationary points. So these are our stationary points. Now, what do we have to do now? Because remember, our question is asking us to find when we're going to get the largest possible. Now, we know that our stationary points can be maximum or minimums. They can also be inflections. So obviously what we're going to have to now do is figure out what are the nature of these stationary points. What are the nature of the stationary points? And you're probably thinking to yourself, oh no, we're going to have to go through this long, painful process of figuring out what both of these points are going to be. But let's, before we do this, consider this for a moment. 12.743. There's something a little bit fishy about this one, which may enable us to reject it straight away. What is fishy about it? Well, let's come over and look at our piece of paper again. And let's come over here. Let's zoom out just a bit. Obviously, there is going to be some restrictions as to what my x can be. For instance, and let me just go full screen here for a second because we don't need the CAS. Obviously, my x is going to have to be greater than 0. I think we can all understand that. The side length of these squares are going to have to be greater than 0. But is there also going to have to be a length that it's smaller than? Or could it just be as big as possible? Obviously, it can't just be as big as possible. I can't have gigantic x's right here. There has to be some kind of limiting factor. And what that is going to be is the fact that both of these sides, this side and this side, are going to have to be greater than 0. So that's going to really tie into things. Because 20 minus 2x is my shorter side, we're going to focus on that. So 20 minus 2x has to be greater than 0. Let's now rearrange this for x. So the first thing that I'm going to do is I'm going to subtract 20 from both sides. And then I'm going to divide both sides by -2, which is going to flip my inequality. And then I'm going to end up with 10 on this side. And as you can see, this is telling me that x has to be less than 10. Now, that makes perfect sense. And the reason why it makes perfect sense is because we know that the width of this piece of paper is 20 centimeters. So if my square was greater than 10 centimeters, it's more than halfway. Things start to break down. So that means my x has to be less than 10. It has to be greater than 0, but less than 10. All right. So that means we can reject this straight away. We don't even have to consider it. We just need to prove now that this is my local maximum. Remembering that's the stationary point that we want here. We want the largest possible, so we want the maximum. So what that means, let me bring this over here. Let me come over here. We're going to have to use one of these tables, and I know this is not people's favorite thing in the world, but we're going to have to use one of these tables to prove that this x value right here is a local maximum. So remember, we put an x here, we put a v dash x here, and we put the shape here. The very first information that we can put is that we know that this is going to be 3.924, and it's actually a bit longer, dot, 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 dot. We know that the derivative for when x is this is 0. Now, what we need to now do is consider points before and after. So what we're going to do is we're going to use our CAS to do that. So let's begin by define our derivative as g of x. That's just going to make our lives a little bit easier. So which one is our derivative? That one right there is our derivative. So we're going to define g of x as that. Done. So we know if we were to go g of x and put in this value right here, 3.92 whatever, we know if we were to do that, we're going to get 0 out. Now, there's obviously more decimal places here. It's obviously just stopped it. So this is as close to 0 as we're going to get, but that is 0. Now, what we're going to do is we're going to consider a point before and after 3.9. So let's consider a point before it. Let's go 3.8. So let's now come to our CAS, 3.8, and then we're going to go equals. And as you can see, I get 13.28. And as we can see, that obviously is a positive number. You can see 13.28 is a positive number, so it means my gradient is increasing. Let's now go a point after 3.924. So let's now try just 4. So we're going to go g of 4, and that should be a negative number, and it is. Let's now put in that information onto my paper over here. Now, as soon as I click off the CAS, my CAS breaks because the CAS hates me. This is going to be 13.28, and on this side, it's going to be -8 for when I put in 4. So this one's going to be positive, then it's going to be flat, then it's going to be negative. So therefore, this right here is going to be a local maximum. So I could say x equals 3.924 is local max. Is a local max. So after doing that, what we can say is that when the side length of my square is 3.924, I'm going to get the largest possible volume. So we could put that in a nice little statement here, as I've already done. So as you can see, when the side length of the square is 3.924, we attain the largest possible volume for the box. And that volume is going to be 1056.3. And we can actually find this quite easily using our CAS now. So we can figure out what the volume is going to be very easily. And the way that we can do that is by graphing our original function right here. So if I go menu, if I go Control, Open Doc, go to a graph and go, I want to graph my v of x, I'm going to get that. That's not going to fit. I'm going to go menu. I'm going to go zoom. I'm going to go zoom fit. There we go. And as you can see, I have a maximum here. I have a minimum here. And if we've done our calculations correctly, our maximum should be 3.924. So this point right here, let's double check that. Analyze graph. Let's go maximum between this point and, between this point and this point. And as you can see right there, we get 3.924. And the volume for when my x is 3.924 will be 1056.3, which is exactly what I've written here. So we can use our CAS to solve that right here. And the other way that we could do it is we could come over here and we could go v of and put in this value right here. We could put that value in. And by doing, we get that number out, 1056.3, right there, by putting in that value. So that was our stationary point. It's our maximum point when x is that. So in other words, when the side length of the square is 3.924, we're going to get the largest possible volume for our box. If we go back to our graph, we also found out that we got a second stationary point here, 12.743, and we said this one didn't make any sense, and sure enough, we have negative volume, which makes no sense. How can you have negative volume? So we were right to reject it, but let's just analyze graph and see that we were correct in our calculations. So this should be 12.743, and sure enough, there it is, 12.743, and you have a negative volume, which makes no sense. Perfect. So we have done everything we needed to for this question. Let's zoom out and marvel at all our hard work. There we go. Hopefully this video was helpful for you in kind of figuring out what optimization problems are all about and how to use your CAS calculator. I'll see you in the next video.